PTO. What's up?
Dude, did you order
man.
the new iPhone 17 Pro? Got it from Verizon, the best 5G network.
Okay. And I don't want top chat, I want all chat. Live chat. Okay. I don't know what happened to the music. Oh, okay. Hey, that's me. Okay.
Using only zeros and ones represent colors, well, by convention, they typically use a system that by an acronym is called RGB, red, green, blue. And this is to say that a computer, to represent a single dot on the screen, maybe this one, this one, this one, will allocate some number of bits or some number of bytes to represent the color of just that there dot, otherwise known as a pixel. You can actually see pixels on your phone or even on your TV or monitor. If you go really close, especially if it's an older monitor, you can see the tiny little squares. Each of those has some number of bits telling the device what color to use. In particular, these devices typically use 3 numbers in total, 3 bytes. So that is to say 24 bits per pixel. And they do this. If you were to represent a single dot on the screen using these 3 numbers, just by intent here, this is 72, 73, known as a pixel. You can actually see pixels on your phone or even on your TV or monitor. If you go really close, especially if it's an older monitor, you can see the tiny little squares. Each of those has some number of bits telling the device what color to use. In particular, these devices typically use 3 numbers in total, 3 bytes. So that is to say 24 bits per pixel, and the device what color to use. In particular, these devices typically use 3 numbers in total, 3 bytes. So that is to say 24 bits per pixel. And they do this. If you were to represent a single dot on the screen using these 3 numbers, just by intent here, this is 72, 73, 33, which in the context of a text message, an email, a Google Doc represents, of course, high textually. What if a computer uses that same pattern of zeros and ones, that is the same pattern of decimal digits, to represent the color on a screen, which is germane if you're opening an image using Photoshop. So using a different piece of software that knows about colors and images and not just text. Well, this would imply that you want that dot on the screen to have like a medium amount of red, a medium amount of green, and a little bit of blue. Why do I see medium and little? Well, again, if each of these numbers is using 8 bits or 1 byte, the highest we can count, as we discovered, was 255. So I'm kind of averaging here. So 72 out of 255 feels to me like a medium amount of red. 33 feels like relatively little blue. But if now the computer combines those wavelengths of light, so to speak, a medium amount of red, medium amount of green, a little bit of blue, what you get is the color code for a single dot. And does anyone want to guess what color roughly this represents? These 3 bytes? Not white, not purple. Not brown. Yellow, in fact, is the answer. So it represents in a single pixel roughly this shade here of yellow. Which is to say, if we look back at any of those emoji, which again are represented by patterns of zeros and ones, but you and I as humans perceive them as images on the screen, let me actually go ahead and zoom in further to one such sample emoji. And when you zoom in far enough, or you put the phone close enough to your face, you can actually see all of those little dots known as pixels, all of the little squares. And given that so many of these pixels are yellow, that is to say that that pattern of 3 bytes, 72, 73, 33, is used to represent this pixel. Another 3 identical bytes are used to represent this pixel, this one, and so forth. So now if you've taken digital photos on your phone or a camera, you're probably generally familiar from the internet and hardware today that a photograph is what, like 1 megabyte, 10 megabytes, depending on the resolution of it. Well, megabyte means millions of bytes. Where are all of these bytes inside of these photographs or these images you're taking or downloading? They correspond to every one of the single pixels on the screen. There's at least 3 bytes being used to represent every one of
each bit. Okay, how would I put this? Each bit has 3 main colors going into every pixel at different amounts or percents. Red, blue, and green, right? Chat, was it green? I can't remember, let me rewind.
one a resolution, one and known as one back at and the end.
Yep. Okay. I should probably put this in the right order. Okay.
And zoom in further to one such sample emoji. And when you zoom in far enough, or you put the phone close enough to your face, you can actually see all of those little dots known as pixels, all of the little squares. And given that so many of these pixels are yellow, that is to say that that pattern of 3 bytes, 72, 73, 33, is used to represent this pixel. Another 3 identical bytes are
You're gonna see what I just typed is what he's about to talk about.
used to represent this pixel, this one, and so forth. So now if you've taken digital photos on your phone or a camera, you're probably generally familiar from the internet and hardware today that a photograph is what, like 1 megabyte, 10 megabytes, depending on the resolution of it. Well, megabyte means millions of bytes. Where are all of these bytes inside of these photographs or these images you're taking or downloading? They correspond to every one of the single pixels on the screen. There's at least 3 bytes being used to represent every one of those dots.
Okay, since this is educational, chat, if you don't know, a byte is 8 numbers, right? So let's say we got 1 through 8, but okay, hold on. Let me think about how to describe this. I'm a little bit sleep deprived right now. Okay, so you have numbers that are represented by a base number, right? That you convert into base 2 from either base 10 or whatever base you're working in. I don't know what base color is in. I think it might be able to convert from base 10, maybe 11. I'm not sure. And correct me if I'm wrong on any of this, because I am not 100% sure on this, but I believe that I'm partially at least correct on this. But so when you store or send data, the computer breaks it into bits, binary digits. Every letter, color, sound, or image is made up of zeros and ones inside the computer. A simple way to remember is base 10 is decimal, right, of digits 0 to 9. Base 2 is binary, which is what the computer actually speaks in and can comprehend. So we will go from base 10, most likely. I mean, as long as it's 0 through 9, and if it's more than that, you'll go to 11 and so forth. Base 2 is what you convert base 10 or whatever other base that you're working into, so that the computer can actually understand it. Computers love base 2 because it matches their on-off system. 0 meaning off, 1 meaning on. So a bit is just a 0 or a 1. 8 bits is a byte. Transistors are things that can be turned on or off, which is what a computer is made up of. This is just a random note that from earlier on. So yeah, I'm not sure exactly what base that the colors are written in. He might say it RGB. I didn't catch if he said it earlier. Let me just go ahead and RGB. Okay, that's bothering me. Oh, this is bothering me too. EL, go. Okay.
As an aside, bit of a white lie, because nowadays there's fancy compression software that can use fewer than that many bytes, but in general, that's where all of those bytes, those millions of bytes, are coming from. So how is that for an answer to how do we represent colors? Thank you. So if we agreed now that there's this way and perhaps others to represent colors, well, how do we represent not just images, but videos? Well, videos, once upon a time, or movies, were called motion pictures. So most pictures with motion. Why is that? Well, it's analogous to growing up. If you ever played with one of these picture books, and in fact, there's memes nowadays that have made these popular again, whereby you have a whole bunch of images on individual sheets of paper, and if you flip through them fast enough, your human mind and eyes perceive it as actual motion, even though you're just seeing image, 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 but it's so fast it looks like motion. That's all a video is on your screen. That's all a film is on your TV. It is not, in fact, continuous motion. It's maybe 30 frames or images per second, maybe 24 frames or images per second, which is to say, we know how to represent numbers, we know how to represent letters, we know how to represent colors and thus images. Now we kind of get videos for free because it's just more of the same. Use more and more of those patterns. Why are videos so darn large? Why are they gigabytes to download? Billions of bytes? Because there's so many darn images, 30 some odd images per second in those kinds of videos. And maybe lastly, just to top off our multimedia, how could you represent sound? maybe musicians in the room, how using only zeros and ones could you represent something as sonorous as music? Something analog as digital, yeah.
Let me think. How would we represent sound? I mean, with zeros and ones, but just a certain pattern of zeros and ones? Wait, what? Files that contain... No? I don't know.
Yeah, so each number that we store in the computer could correspond to a certain frequency, which has a direct relationship to the sound or the pitch of a note. For instance, in the world of piano and many other instruments, you've got like your A, your B, your C. Maybe you have sharps and flats as well. We could just agree, like the ASCII people did years ago, to represent the musical note A, let's use this pattern. Musical note A sharp, let's use this pattern, and so forth. But maybe pitch alone or frequency alone is not enough. Maybe we need that number, but maybe a second number for the volume, the sort of digital equivalent of how hard are you hitting the key on the piano. Maybe a third number for how long are you holding the key down. So maybe the pitch and the volume and the duration, kind of like RGB, we could use 3 bytes to represent every musical note in some piece. And if we wanted to keep track of what instrument should be played by the computer to sound that music, well, maybe that's just a 4th byte or something else as well. Which is to say, at the end of the day, all we have are these zeros and ones to throw at the problem. So for now, that's it for representing information. We've got our numbers, we've got our letters, we've got our colors and images, our videos, and now sound. Any questions on how computers then?
Chat, good question. Are there any questions on, like, do you have any questions? Whoever's watching. Whoa, don't show that. Okay. I'm about to move on. I don't know how much of a delay there is. I don't know if you're asleep or not. Whoever's in here, I don't know if there's actually somebody in here or not. Or if it's me. Twice. But
Are representing, as promised, those inputs and outputs. Using
oh, so earlier. Boom. That's this.
just zeros and ones. Yeah, in the middle.
Which this is problem solving in an image. Which he would probably go into more detail into here.
Correct. So the computer is taking as input at the end of the day zeros and ones and is outputting zeros and ones. However, as we'll learn in this class, by writing software, by writing code that understands those zeros and ones, we will enjoy not just literally seeing zeros and ones, we will see A, B, C, we will see colors, we will see video, we will hear sounds, so long as we write the code to interpret those zeros and ones. And indeed, it's worth noting now that that same pattern I keep using for an example, 72, 73, 33. How does a computer know? Is that the message high? Is that the color yellow? Is it a dot in a video alone? just depends on the context. Simply put, if you're opening that pattern of zeros and ones with like Excel or a calculator program, odds are the software will interpret those 3 bytes as numbers, of course. If, though, you open that same pattern in a text messaging program, Google Docs, Microsoft Word, that same pattern will be interpreted as a sequence of letters. Instead, if you open Photoshop that same pattern, you'll probably see a single dot that happens to be yellow. Conversely, once you yourself are a programmer, or even better programmer, you will be able to write in code how you want the computer to treat these patterns of zeros and ones. You can essentially tell the computer, use this to store a number, or a letter, or a color, or something else. That's the power the programmer themselves have at the end of the day. Other questions on representing things with bits? No? All right, so lastly then, in this middle of this black box, so to speak, is the sort of secret sauce that solves problems, that converts those inputs to outputs, those problems to solutions. So what is an algorithm? It's really just step-by-step instructions for solving some problem. And indeed, I think back to my own first time in CS50, where we learned the same from Professor Brian Kernighan, and as luck would have it, just had my 25th reunion where we pulled some video footage from 1996, and so we're actually fortunate to have the very first few minutes of CS50 over 25 years ago when I myself took it, but the lessons back then as today are fundamentally the same. And what's important indeed is to not only express yourself correctly, but precisely, as we'll explore today. This then is Professor Brian Kernighan, who years ago very memorably introduced us and my classmates to algorithms by actually in class shaving his beard. If we could dim the lights here for Brian.
The other thing that we're going to talk about in this class is the notion of an algorithm. An algorithm is a very precise description of how to do something. And the operative word there is precise. Okay, it has to be very, 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 very precise. And the task that I'm going to do is that I'm going to trim my beard, which has gotten out of whack. And I brought a variety of things which one might use to trim beards with
So suffice it to say, I don't have much of a beard, but I do have this here other technology known once upon a time as a phone book. And these phone books, of course, have lots of information in them, happen to be storing numbers and letters in particular. For those unfamiliar, they are storing humans' names from A to Z here in English, and associated with everyone's name is a number. So even if you've never had occasion to physically use this kind of device, turns out it's pretty much equivalent to the contacts or the address book app on your iOS phone or your Android phone as well. Why? Because if you pull up your contacts, of course, you see some familiar names here alphabetized by first name or last name. And if you click on any of those names, you reach the person you're presumably trying to call or text. Pictured here then is John Harvard's, whose number here is +1 949 468 2750, which you're welcome to call or text at your leisure. But here is John Harvard that's partway through the phone book digitally. Well, it turns out that physically in the phone book, we might use an algorithm, step-by-step instructions for finding John Harvard in pretty much the same way as iOS, Android, macOS, Windows, or other operating systems themselves use. So I could, when looking for John Harvard, first name starting with J, I could start at the beginning of the phone book and start looking page by page for John Harvard. And if he's there, I can call. This is an algorithm. It's indeed step by step. Well, that was a bug. A few pages turned. But is this algorithm correct? Step by step, assuming I'm paying attention. So yes, like if John Harvard is in here, I will eventually find him once I get to the J section. Now, this is a little tedious. It's going to take like a while, few hundred pages. So maybe I could do things a little smarter from grade school, like 2, 4, 6, 8, 10, 12, 14, 16, and so forth, going twice as fast. Is that algorithm correct?
No.
So no, but why? I could miss him, right? I could just get unlucky, really with 50-50 probability, because John Harvard could be sandwiched between two pages. Now, this isn't a complete loss, this algorithm. Maybe what I could do is, if I get past the J section to like K, I could double back at least one page just to make sure I didn't miss John Harvard. So I can still go twice as fast, plus like an extra step just to make sure I didn't mess up. So the first algorithm might take as many pages as there are in the phone book. So if this phone book has 1,000 pages, in the worst case, if I'm not looking for John Harvard, but someone whose name starts with Z, might take me 1,000 pages to actually get there. Second algorithm, twice as fast literally, might take me 500 plus one step to get there because I'm going 2 at a time, so long as I indeed fix that bug. But what we used to do back in the day, and what your phone is doing today, albeit digitally, is going roughly to the middle of the phone book, looking down and realizing, oh, I'm accidentally in the M section, so halfway through the phone book. But what do I now know about John Harvard? Is he to the left or to the right? So he's obviously to the left because J comes before M. So what I can do literally, and what your computer does figuratively, is tear the problem in half, throw half of the problem away, leaving us now with the same fundamental problem, but it's half as big. So I've gone from 1,000 pages suddenly to 500 pages, and compare this to the other two. 1,000 pages, 999, 998, versus 1,000 pages, 998, 996, 994. That's still slow. I went from 1,000 to 500 in just one step of this algorithm. What do I do next? I go roughly to the middle here. Oh, I went a little too far. I'm in the E section now. So is John Harvard to the left or right now? So he's to the right, so I can again tear the problem in half, throw the left half away, knowing now that John Harvard must alphabetically be in here. And I can divide and divide and divide and conquer this problem again and again by using that heuristic of going left or going right. And I dare say if I do this correctly, I'll eventually be left with one single page on which John Harvard's number actually is, or maybe he's not in the phone book at all. So how many steps maximally might that third and final algorithm take? It's not 1,000, it's not even 500 or 501. How many times can you divide 1,000 pages in half again and again and again?
Okay, 1,000 divided by 50%. Oh, what's that fucking thing called? Oh my god, I'm like botting out right now. Square root. Fuck. So if you square root, the square root of no. Yeah, what's the square root of 1,000? One? Oh, 31. 31. So 32, round up.
Roughly.
32. That's your answer.
9, 10, so well, typically 10 times, give or take. There's a bit of rounding there because it's not a perfect power of 2, but roughly 10 times. Like, that is fundamentally better than both of the two algorithms because I go from 1,000 pages to 500 to 250 to 125 and so forth.
Okay, if you didn't catch what happened right there, 10 to the power of 2. Power of 2 is 10 times 10, which is 1,000. Thereby only allowing 10 times for you to be able for the maximum amount of attempts before it either finds the contact or file or not. Boom. Okay, so the other person left, but it's okay. We'll get more viewers soon.
Daily cash back
I'm trying to give my 2 cents here.
Subject to credit approval.
Good.
Apple Card issued by Goldman Sachs Bank USA, Salt Lake City branch.
I wish this
Terms
would go
and
fast
more at
real quick so I could just
applecard.com.
fucking talk. Thank you. So 10 to the power of 2 is 10 times 10, which is 1,000. Thereby only allowing the maximum amount of attempts before the computer either finds a contact or the file is 10.
Literally having the problem again and again. So we can actually appreciate and see this even more so graphically, and this is among the things we'll do later in the term when we speak to not only writing correct code, but is your code well designed? Is it better than your previous code? Is it better than someone else's code? Is it better than some other product? If you have given more thought to the algorithms and the quality thereof, you can perhaps minimize the time required to solve problems, but no less correctly. So if we have a simple XY plot here, on the y-axis or vertical is the amount of time to solve in whatever unit of measure, seconds, pages, however you want to count. On the horizontal or x-axis is the size of the problem, measured in, for instance, numbers of pages. So this would mean 0 pages in the phone book. This would mean a lot of pages in the phone book. This would mean no time to solve. This would mean a lot of time to solve. What's the relationship then among those three algorithms? Well, the first one is essentially a straight line, a slope of 1. And if the phone book has n pages in it, we'll describe the slope here as essentially 1/1 for the algorithm with the first algorithm, turning page by page by page, which is to say, if we were to add one more page to the phone book next year, first algorithm is going to take one more step. But the second algorithm is definitely better. It's definitely faster, but it's still a straight line. So it's going to take roughly n/2 steps on average, because you only have to go through half of the phone book because you're going 2 pages at a time, instead of the whole phone book in the worst case if someone its name is Z, to go through every page in total. So if we actually compare these, let me just draw some dashed lines. Suppose that you have this many pages in the phone book. If you just draw this vertical white line here, it's going to take this much time in red using the first algorithm, but it's going to literally take half as much time in yellow for the second algorithm, because you're literally going 2 pages at once. Red using the first algorithm, but it's going to literally take half as much time in yellow for the second algorithm, because you're literally going 2 pages at once. But the third and final algorithm is a fundamentally different shape. It instead looks a little something like this.
Okay. That's Pac-Man. Where is it at though? I'm not seeing this on the keyboard. Oh, I can just fucking do this. Oh, hey, 2. Okay. Base 2.
Looks like it's flatter and flatter and flatter. It's always increasing. It never gets perfectly flat, but it grows so much more slowly as a function of phone book size. And for those who recall their logarithms, this would be described as log base 2 of n. And in fact, that's where the math came from. Log base 2 of 1,000 is roughly 10 in total, even if you need a calculator to confirm as much. But this shape is fundamentally different. Why? Well, suppose that Cambridge, where we are, and Alston, the town across the street next year, combine their 2 phone books, and they go from 1,000 pages each to 1 phone book with 2,000 pages. The first algorithm is going to literally take twice as many steps or pages. Second algorithm is going to take half as many, or 50% more, because you're going 2 at a time. But the third algorithm is going to barely miss a beat. Why? Because if this is 1,000 pages here, and 2,000 pages is over there, just inferring from the shape of the green line, it's not going to be much higher on the vertical axis than the other two were. So more specifically, if you have a 2,000 page phone book next year, how many more steps will it take you using that third and final algorithm? Just one, because you'll divide and conquer a 2,000 page phone book into a 1,000 page phone book, and then you're back at the original story. And that's the sort of power of learning algorithms. That's the power of learning computer science and learning how to program, is to be able to navigate big data, so to speak, things the size of Google, things the size of artificial intelligence training data sets, using better and better, more clever algorithms that perform faster and therefore not only make the software more competitive, but also make it more usable and more favorable for people like you and me when using that software. So when it comes to implementing algorithms as programmers, as computer scientists, what you're really doing is taking these algorithms, which might be expressed in English conceptually as we just did, but really just translating them to code, be it C or C++ or Python or R or Ruby or any number of other languages that exist in the world. But for now, let's consider how we might implement that algorithm using something that's literally still English, but pseudocode. Something that is still correct, but precise and finite, as per Professor Kernighan's advice, which is to say, use your own vernacular of English and just say what you mean, but very succinctly. There's no one way to write pseudocode. It's not some formal language. I'm just going to convert the steps I did intuitively to step-by-step instructions as follows. Step one, what I did was pretty much pick up the phone book. Step two, what I did was pretty much open to middle of phone book for the third algorithm. Step three, look at page. Step four, if person is on page, then step five.
Yo, what's up, chat? How we doing?
Start the season with Etsy and make your holiday traditions extra special. On Etsy, you'll discover original pieces.
Call person. If that does not prove to be the case, step six, else if the person is earlier in the book, then open to the middle of the left half of the book, and then go back to line 3. Then, if the person is later in the book, open to the middle of the right half of the book, and again go to line 3. Else, there's a fourth and final case.
else if person is later in book. 10 open to later in book in whoops middle of right of the book.
Case, if the person like John Harvard is not on the page, is not earlier, is not later, what's the fourth scenario we'd best consider? He's just not there, else we should do something specific like quit. Now, as an aside, everyone in this room has probably had one of these stupid technical support issues where your phone or your laptop or your desktop computer just freeze all of a sudden, or maybe it spontaneously reboots for no reason. Odds are that's because not you, but some other human made a mistake. They probably wrote code working at Microsoft or Apple or Google or somewhere else, and they didn't actually anticipate that, oh, there could be a fourth scenario that could happen in the real world. But if there's no code that tells the computer what to do in that fourth and final scenario, who knows what the computer is going to do? It might by default reboot, it might by default freeze. That's just a hint of the bugs, the mistakes in software to come. But even though this is just one way to write this code, aka pseudocode, there are some salient characteristics that we'll use throughout today. One, there are these verbs, these actions, and henceforth, as aspiring computer scientists or programmers, we're going to start to call these by what more technical audience would. These are functions.
Functions.
A function is an action or a verb.
Come on now. Hey,
it's like a
listen. I got at least a little bit of prior knowledge.
bite-sized task that a computer can do for you. Those then are functions in this here pseudocode. But there's other types of code in here. There are these things here, if, else if, else if, else. Those are examples of what we're going to start calling conditionals. These are sort of proverbial forks in the road where maybe you go this way, maybe you go this way, but you decide which way to go based on a question. The questions that you ask are what we'll technically call Boolean expressions, named after mathematician Boole. A Boolean expression is a question with a yes or no answer, a true or false answer, a black or white answer, a 1 or 0 answer. There's two possibilities, and there's a hint of the binary underneath. A Boolean expression is going to tell you yes or no. You should go down that fork in the road. Notice what's important here is that indentation mattered as a result. Yep. Notice that on line 4, when I first asked if the person is on page, question mark, so to speak, I should only do line 5 per its indentation if the answer is yes or true. I should only open to the middle of the left half of the book and go back to line 3 if person is instead earlier in the book. So indentation in pseudocode and in many programming languages has logical significance. It tells you whether to do things or not.
Type shit.
But there's another construct in here, go back to, which literally makes me go back to line 3, potentially again and again and again, creating some kind of cycle, or what we'll typically call a loop instead.
Chad, this is what I'm
So
talking about.
even in this
got
relatively
knowledge.
simple real-world algorithm,
knowledge.
we have these 4 fundamental characteristics of most computer programs that we will write in this class, and you might
garage.
write beyond this class, that we have some technical jargon now to describe them. But what's important to note is that line 8 and line 11, even though they're saying go back to line 3, go back to line 3, you might think you're running the risk of what we'll call an infinite loop, where you literally get stuck in a loop forever, which doesn't sound like a good thing if at some point you want to turn your computer off, even though it's still working. But these will not induce infinite loops. Why? What is happening in this particular algorithm every time we go back to line 3 that guarantees eventually we will stop going back to line 3?
If the person is earlier in the book, go back to...
Exactly. If the person is on the page, we will call them or we will quit. But more importantly, because we keep dividing and conquering the problem, in this case, having the phone book, eventually we're going to run out of phone book, in which case, indeed, John Harbert is either on that page or not.
So it's only going to cycle 10 times.
And we will call or we will quit instead. So we'll see in time, and in fact, allow me to promise, odds are at some point you will write code that seems to take control of the computer for you, where it's doing something, and it literally won't respond to you anymore. That's just going to be because...
Let me ask ChatGPT. Would this code only repeat 10 times? Excuse me, chat. Let's see. I'm trying to study. Why is it slow only whenever I'm streaming? Usually this shit's quick as fuck. Come on. Oh, okay. So I was wrong. So it depends. The cycle will repeat depending on the size of the phone book, but not infinitely. And I even spelled that shit right. Come on, bruh. Chat, yo, we're high.
Because of a mistake, a so-called bug that you yourself will invariably have added to your code accidentally, but we'll show you ways for terminating it or breaking out of those conditions. And indeed, what we'll do in just a little bit after a break for today's lecture is explore not just these concepts, but some of the ways you can use them to solve real and very visual and audio problems. But for now, let's at least connect it to something that's been all too germane in recent months, the past few years, namely artificial intelligence, which is a topic we'll come back to at the end of the course too, to give you a sense of like what the connection is with what everyone's been talking about in the world of AI and what it is we're going to spend the next few weeks building up to by writing code. If you were to try to implement something like a chat bot, for instance, that just answers questions and has a conversation with you, you could do that using pseudocode. And as we'll soon see, you can use C, Python, any number of other languages too. That pseudocode might look like this when implementing a chatbot. You could tell the chatbot if the student says hello to you, then say hello back. And the indentation, as per earlier, implies this is conditional. Else, if the student says goodbye to you, say goodbye to the student. Else, if the student asks you how you are,
It's JCPenney's really big deals and comedian Bonnie McFarlane.
I've been thinking a lot about bags. I'm the dreaded bag in a bag in a bag lady. I put another bag inside of that.
This weekend, buy one bag, get one free. Yes, JCPenney. Limited time specials excluded from coupons. Ends 11/2.
When too much work bogs you down, Asana helps you handle it. AI makes it easy to hand off routine
say
tasks.
you are well, so you can just enumerate question after question after question and just handle all of these conditional possibilities. But things kind of escalate quickly, especially with the tools of today like ChatGPT. Are we really going to have the wherewithal as programmers to write another conditional like else if the student asks why 111 in binary is 7 in decimal? Like, this kind of hints at, oh my God, there's like an infinite number of things this human could ask the chatbot. Do we really have to write an infinite number of conditionals? Like, that's just not possible. Like, there's not enough time in the day. There's not enough lines of code available. Artificial intelligence surely needs to be able to figure some of this out instead. And so indeed, this is not how you implement AI, but rather how you implement an AI like a chatbot is you typically train it based on lots and lots of data. You give it lots of inputs, training data, and let it figure out what it should say in response to certain questions. And it boils down to a lot of probability, a lot of statistics, otherwise known now as large language models, which if we really peek under the hood, are actually typically implemented with what are called neural networks, inspired by the world of biology, whereby we humans have all of these neurons that transmit electrical signals such that my brain tells my hand to move this way, and this other way. And so what computer scientists have been doing over the past many years is implementing in software, using literally zeros and ones, graphs or networks, neural networks that look a little something like this, where each of the circles represents a neuron, each of the arrows represents a pathway between them, and provides as input to these networks huge amounts of data, like all of the internet, all of Wikipedia, all of the books that it might consume as input. And then the goal of this neural network, as per this single final neuron right here, is to produce an answer to a question. Maybe it's simple, like yes, no, or maybe it's something like the answer to the 111 question, or how are you, or goodbye, or hello, or the like. And what these neural networks do is use statistics and probability and try to output the most probabilistically likely answer to this question that's been asked and really just hope that it is correct. There's no program where it opens.
Okay, let me rewind that for a second. Sorry, guys.
Likely answer to this question that's been asked and really just hope that it is correct. There's no programmer at OpenAI or Google or Microsoft that's trying to anticipate every one of these questions we might ask, not only in English, but in other languages as well. So you might be wondering why there's this like 8-foot duck on the stage. So the persona that CS50's own AI takes is in fact that of a rubber duck, because it turns out in programming circles, and this is true long before CS50, it has often been recommended to students and aspiring
questions so far?
Programmers that you keep like literally a physical rubber duck on your desk. The idea being, in the absence of a friend, family member, colleague, TA, who could answer technical questions for you. If you're alone in your room in Mather at night, you can sort of talk to the duck, maybe door closed, and ask the duck your questions, or more importantly, talk the duck through what confusion you're having. And the mere act of talking through the problem, explaining logically what you're trying to do, what you're actually doing, and what the error actually is, invariably that sort of proverbial light bulb goes off and you realize, oh, I'm an idiot. I hear in my own words where I've gone awry. And even though this duck will never say anything back to you, that alone, rubber duck debugging or rubber ducking, tends to be a valuable programming technique, believe it or not. But thanks to these large language models, we have not only physical but virtual ducks as well. And so available to you will be in this class not tools like ChatGPT and the like, which are through policy disallowed. It is not reasonable to use ChatGPT and the like, but you are allowed and encouraged to use CS50's own AI-based tools, which resemble those same tools, but know something about CS50 and aspire to behave akin to a good teaching fellow, guiding you to solutions as opposed to handing you something outright. So this is a tool that will be available at literally this URL throughout the course, cs50.ai. It will also be embedded in the programming environment you'll soon meet, which is called Visual Studio Code, a cloud-based version thereof. The duck will live in that environment as well as on stage from time to time, which is to say, we'll not only talk about, but use throughout the course this thing known as AI. But this is ultimately code that we're going to start writing next week. And unfortunately, this code here is written in a language called C. This is essentially the program that I lost 2 points on, like some 25 plus years ago. And it does look admittedly cryptic. And that's why today what we'll focus on is not what this code looks like, nor the zeros and ones that code gets.
Holy shit. Chat, are you seeing this fucking code that it gets translated into? Oh my god. Look at that. That's fucking crazy. Okay, let me get this down real quick. Integer main. We're gonna avoid this. So this is a prompt for it to print. Hello world. We're gonna do a fucking weird ass / for some reason, in quote, end it with a semicolon, go back down here and end the prompt. In this print hello world. Holy shit, so this is C. That's fucking, bro, just to do that is insane.
like, nor the zeros and ones that that code gets converted to so your computer can understand as input what you want it to do. We're going to focus on a much more visual incarnation of this, but I know thus far this has been a lot. So let's go ahead and take a 5-minute break here, and when we come back in 5, we'll do some actual programming. So see you in 5.
Okay, chat, I think that is where we're going to leave off. These are the finalized notes for today. Some written, unfortunately, by ChatGPT. I did not know that it was not reasonable at the time of using ChatGPT. I did not use it for any like questions or answers. The only thing that I did do was use it to get a better understanding of what it is that he was actually talking about, such as base 2 and the meaning behind it. And once I did get a better understanding on that, I used it for bits, for it to describe bits and transistors, things like that. But after that, that is the last time I used it, and ever since then I've been only taking notes. As you can see, although this is mine, I created this myself and did all of this. All me right here, baby. So, tomorrow I am going to wake up probably about 10 a.m. Unfortunately, that's my sleep schedule right now. It's 1 o'clock in the morning where I'm at. I mean, 12:50 a.m. Happy Halloween, everybody! Happy Halloween. We made it to Halloween, and we were coding on the switchover, so that seems pretty nice. Anyways, I hope you guys enjoyed. If you guys missed some of it, you can go back and rewatch everything that I have studied in this session. It was only an hour session long for the live. I was recording for 20 minutes before that, but that was for like 5 or 10 minutes, so that was just me setting up stream. But other than that, I will catch you guys in the next one. It was actually a pretty fucking decent stream. I was not expecting so many people to be just hopping in. Like I'm getting a lot of fucking viewers. It's pretty fucking crazy. I'm gonna start streaming on YouTube more.